All right. Last time we talked about susceptibility, response, correlations, and we computed those things in the case of the Ising model with a discrete symmetry. And then we went back and started looking at the ON model with a continuous symmetry. I'm going to go and just grab a picture and stick it in the lecture. Where's my picture? Way back, this picture. Let's take that. And then back up here. Let's put it there for now. Okay, so what we did last time, at the end of last lecture, what we did was we looked at the ON model. We imagined that we were applying an external magnetic field in a particular direction in spin space. And then we started defining correlation functions. And the correlation functions were defined, some that were parallel to the direction of ordering, and one was transverse to the direction of ordering. And earlier in the lecture, I'd shown you that there's a connection between the integral over space of the correlation function and the susceptibility that you measure in thermodynamics. And we guessed that there would be such a thing also for the case when you have a continuous symmetry. For now, we've got two types of correlation function: longitudinal, where you're looking at correlations in the direction of ordering, and transverse, where you're looking at directions perpendicular to the direction of ordering. So what we're going to do today is we're going to work out the susceptibility tensor for the ON model. I'm going to show you how from that we can very quickly estimate the qualitative properties of the excitation spectrum, and we're going to prove for you the existence of modes called Goldstone modes. I'm going to show you that they are related to the nature of the correlation functions below TC, and I'm going to show you at the end, if we have time, how rigidity emerges from this description. So the very last thing that we did was we just defined the transverse correlation functions, which you can see over here on the left hand page. Okay, so let's get started. And where I'm going to start is with the susceptibility tensor. So what we're going to do is we're going to define. It'd be great if I had a pen. Oh man, what the heck? What is going on today? Okay. All right. Okay. I don't understand what is happening. All right. Okay, let me just check the Zoom is still recording. Zoom is recording. Great. Okay. All right. So we're going to define the susceptibility tensor. And I'm going to define it. I've got a minus sign in this definition, and I don't know whether it is correct or not. So I'm going to follow it. If you go back and look at this calculation later, you might want to check that minus sign. Okay, so susceptibility says if I take an order parameter, the magnetization, now I'm going to ask the question, how does that magnetization change when I apply an external field? That's the thermodynamic definition of susceptibility for a magnet. So now we have a system which orders in n dimensions in spin space. So I've got the alpha component of the magnetization, which is a vector, and it's differentiated with respect to the beta component of the external magnetic field. And so this thing then is a tensor chi alpha beta. And this thing is equal to, because dm by dh is minus df by dh, I think that this thing, well, maybe this one may not be right. This one probably is right. This is d2f by dh alpha dh beta. That's because the magnetization is minus df by dh. And so when I look at how the magnetization changes with h, then I get a second derivative. So, so the magnetization alpha is minus df by dh alpha, and f is the free energy per unit volume. So chi alpha beta answers the question of how much does the alpha-th component of magnetization, order parameter more generally, change when the beta component of the external field changes. That's what this quantity represents. And this is page 93. And so this is page 94. Okay, so here is the key step here. So the key step is that the ON model is symmetric under rotations in spin space. At least when there's no external field being applied. So what that means is that the Hamiltonian of the system, I have my order parameter S. That means that this thing means that the free energy per unit volume cannot depend on the direction of H when I set H equal to, when H is non-zero. So I've got a free energy, a Hamiltonian that is rotationally symmetric. Whichever way I apply the external field, this way, or this way, or this way, it's still being applied on top of a symmetrical Hamiltonian. And so the answer must be that whatever happens cannot depend on the direction of the field, it can only depend on its magnitude. So what that means is that the free energy per unit volume, which in principle is a function of the vector h, is actually a function of the magnitude of h. Okay, so h by h I mean the magnitude of the vector h. Okay, now that simple fact has amazing consequences. So let me just make sure we understand that what the absolute value is the sum from 1 to n, the sum of the vector components squared, square root. If you had a vector in 2 dimensions, this would be x squared plus y squared, square root. That would be the magnitude of the vector r, for example. So the magnitude of an n-dimensional vector in spin space is the sum of the components h1 squared plus h2 squared plus h3 squared all the way up to hn squared, and then take the square root of that. That's the magnitude. So what that means is the following. We have some very simple calculus identities. So that means that d by dh alpha, and why do I care about d by dh alpha? Well, because over here, we are considering derivatives with respect to the external fields. So d by dh alpha is equal to d by dh times dh by dh alpha by the chain rule. And this is just h alpha over h times d by dh. Okay, so that's just from the chain rule. So that means that if I were to compute now chi alpha beta, So this is equal to minus d by dh alpha of d by dh beta of the free energy. D by dh beta of the free energy is h beta over h df by dh. And so now I'm going to differentiate these terms. So let's just first of all do a quick quiz. So the first term I'm going to have is d by dh beta, sorry, d by dh alpha of dh beta. So let's just make sure that everybody knows what that is. So we're going to have to compute terms such as dh beta by dh alpha. And what does this thing equal? So some of you know the answer, and some of you don't know the answer. Work it out. You know the answer. You know the answer. You know the answer. Right? You know the answer. EJ, you know the answer. Yeah. Okay. You guys. Okay. dh by dh alpha. Beta can be any number from 1 to n. It means a component, one of the components, say x, y, z. Okay. So this would be like saying dx by dy. I've got a vector r, dx by dy. X and y are independent variables. So dx by dy is equal to what? 0. And what is dx by dx? 1, exactly. So dh beta by dh alpha is what? Yeah, exactly. So that would be delta alpha beta. Okay. So that's the only thing you have to know here. So now let's go back and compute this derivative over here. So what we're going to get is the following. I'm going to write out all the terms for you and then I'll put them all together. So I'm going to get minus delta alpha beta 1 over h df by dh. So that's the dh by d alpha acting on h beta. And then I have another term, which is h alpha h beta over h squared times 1 over h minus df by dh. And then I have a term minus h alpha h beta over h squared d2f by dh squared. Now let's put those together. So now what I get is minus h alpha h beta over h squared d2f by dh squared minus 1 over h df by dh times delta alpha beta minus h alpha h beta over h squared. So imagine that the vector h is the magnitude of h times the unit vector in which you're applying that vector. So then what that means is h alpha h beta over h squared is the alpha component of this unit vector times the beta component of this unit vector. And so what I've just shown you is that the susceptibility tensor chi alpha beta is equal to n alpha n beta times a number, which I'm going to call chi parallel of h, plus chi perpendicular of h times delta alpha beta minus n alpha n beta. So it has this particular tensor structure, and we can read off from the calculations that we just did that the parallel component, chi parallel of h, is just minus d2f by dh squared, and the perpendicular component of this tensor, chi perpendicular, is minus 1 over h df by dh. So this is the tensor decomposition, and this all just follows purely from symmetry. So what you're supposed to understand by this is that if h is parallel to m, then that gives you what you measure is chi parallel, And if H is perpendicular to M, then what you're measuring is chi perpendicular. All right. So this is the result. Now, I want to point out to you that this term over here, you've seen before. What is df by dh? Or minus df by dh? So if you look over on the previous page, df by dh minus df by dh is m alpha. So what this term is, the term I've just calculated, this term over here is actually m over h. And this is going to have a very important consequence. Okay, so let's go and work out what that consequence is. So this is now section 11.1.2 in 11.1.2. So that we're going to look at the excitation spectrum. The ON model. For T less than TC. So we're going to now suppose that the system has ordered. And so that means that there is an M not equal to 0. The M is pointing in a certain direction, and that is true even when there's no external field H is equal to 0. So what that means is that if I look at chi perpendicular of H equals 0, so that is equal to M over H. H is 0, so that is equal to infinity. Or another way to say it is chi perpendicular of 0 field is equal to 0. Sorry, minus 1. So since the susceptibility is equal to the zeroth component of the 2-point correlation function, that means that the 2-point correlation function in the transverse direction evaluated at k equals 0, that itself is equal to 0. Okay, so we've now deduced something about the transverse correlations in the system from this very simple statement about the thermodynamics. So just to recap, just to remind you, what we did last time was we proved that if I take the integral of the 2-point correlation function, look here on the left-hand side, the integral of the 2-point correlation function, I showed you how to do this, and that is equal to the isothermal susceptibility times a factor of kT. And the integral of the correlation function in real space is just the k equals 0 component of the Fourier transform of it in k space. So what I've just deduced is that the 2-point correlation function at k equals 0 is equal to 0, and we're going to, the inverse of that is equal to 0, and we're going to have to figure out what that means. Now, let's have a look at the physical interpretation. Now I want to grab this picture. I keep trying to grab it and copy, put it over here. All right. All right, so here. Go away. I don't want to. Okay, aren't you glad you saw that? All right, so what does this mean? The susceptibility in the transverse direction is equal to infinity. So this over here, what it means is that if I have an infinitesimal field, transverse to the direction of ordering, it can move the order direction by a finite amount. That's what we mean when we say something has an infinite susceptibility. Infinite susceptibility means that the slightest push will have an order one effect, a magnitude effect. If I balance this pencil on its tip like this, which of course I'm not able to do, okay, it's in an unstable equilibrium. If one atom of air flies into this and pushes it, it will fall over. The infinitesimal kick will have a magnitude. So what we've shown here is we've calculated the infinitesimal field transverse to the direction of ordering will move the ordering direction by a finite amount. So let's have a look then at this picture. It's very easy for us to see what this means. So here we are in the ordered phase. Here is the direction of ordering, like so. If I apply a transverse field, that transverse field is going along like this in the around this minimum, and the point is this: this minimum here, this minimum going along the bottom here, this minimum is infinitely degenerate. That means those states all have the same energy. So it costs me no energy to rotate the direction of ordering. And that's why I don't need a finite amount of push to make the direction of ordering change. So this divergent transverse susceptibility is really a consequence of the infinite degeneracy of the ordering. So let me write that down. So this infinite transverse susceptibility is a consequence of the infinitely degenerate minima of the Landau free energy, or the effective Hamiltonian, below TC. Not true above TC. When you're above TC, you have the picture on the left, and there's only one minimum at S equals 0. But while I'm below TC, then I have this infinite degeneracy. So when we have ON symmetry spontaneously broken, then we can have two kinds of fluctuations. And those two kinds of fluctuations are fluctuations in the direction of ordering, the longitudinal direction, and fluctuations in the transverse direction. And so we're going to look at those separately. So these two different kinds of fluctuations are fluctuations in the direction of ordering, and I can have fluctuations transverse to the direction of ordering. So that those are the two possibilities that can happen. These ones here, these change the magnitude of the ordering vector. So these change the magnitude of S. These ones over here change the orientation, or if you like, the phase of the ordering vector. Now, if you look at the picture, I want you to imagine what the I want you to imagine what happens when we change the magnitude. So let me draw a cross section through this this picture. Yeah, that's a bad picture. Let's do it again. Okay, so this is V of S. I'm drawing here the ordering direction S1, and out here is the ordering direction S2. So you should think of this picture as having some degeneracy like that, and this whole picture is rotated around this axis, just like is drawn on the left-hand side. So what happens when I make a change in the ordering in the magnitude? So the order parameter, the magnitude of it is here. It's that vector like so. And if I change the magnitude of it, so it's sitting right here. So if I change the magnitude, then it's going to either go up to here, or if I make the magnitude smaller, the energy is going to go up to here. So what we can see from this picture is that a change in the magnitude of the ordering costs energy, just from the potential. But on the other hand, if I make a change in the transverse direction, which I'm trying to draw like that, a change in the phase of S costs no energy. Okay. So everything I've drawn on the left-hand side is all true for a spatially homogeneous system. We don't have a spatially uniform system. We have a system which has got thermal fluctuations. So at different points in space, the order parameter of S has different values, different directions, different magnitude. It's fluctuating. And if I looked at it over time, I'd see it fluctuating like this, like the surface of the ocean fluctuating like that. And so we don't have a spatially uniform system. We have spatial fluctuations in the magnitude and the orientation, and therefore spatial fluctuations in the gradient of the order parameter. So now the question is, what happens when we include spatial variations? Well, we know what the answer to that is, because we simply go back a few pages and we look at our Landau free energy. So let's see, somewhere we'll find it. Here it is, over on the left-hand side. So this is the Landau free energy over here on the left, up at the top. That's the case for a scalar system. For a system which has got, for the ON model, its free energy is 1 million miles back in the past. Where do I find it? Well, somewhere close to here. Okay. Here. Right. So here is the free energy for the ON model. So we have the scalar terms like this, and then we have the gradient terms which are there at the top of the page. So those gradient terms, those come in so this is the total Landau free energy. So we have the potential terms, which what we've been drawing before, and now we have to include these spatial gradients which come in over here. Okay, so let's skip forward 30 pages. And let's continue to calculate them. So what that term is we need to include this term, the grad s squared, integrated over the volume. And let's have a look at qualitatively at what this means. So if I think of this as being grad s squared, as being, take its Fourier transform, that would be k squared times s squared, sk squared. Of course, there's going to be directional terms in that, so we'll do that more carefully in a minute. But basically, this is going as k squared. So what happens is this: the longer the wavelength of the transverse fluctuations, the smaller is the energy cost. So you can see that if s is equal to a constant, grad s squared is equal to 0. If s is varying very slowly with some very long wavelength, then grad s will be a small number. We're going to square it, and so we'll get that number squared. If grad s is varying very rapidly, so we can think of this as being k squared sk squared. So for k going to 0, the energy is going to 0 as k increases. In other words, higher k means smaller wavelength. Then the energy cost goes up. So what that means is that if I were to compute the excitation spectrum of the system, so I say to you, here is a mode that has wave number k. I want to compute the energy spectrum of that. How much does that thing cost? We know that the longitudinal modes, even if they have no wave number dependence whatsoever, even if it's just spatially uniform, the longitudinal modes always have a finite energy cost. So the longitudinal mode, even at k equals 0, which means spatially uniform, it has an energy cost. So that is a gap. And then if I make the wave number greater, the energy cost is going to be greater still. And so it's going to go like that. So this is going to be the spectrum for the longitudinal fluctuations. But on the other hand, if I'm looking at the transverse fluctuations, when the system is spatially uniform, they cost no energy. As I start to make the wavelength smaller and smaller, meaning k gets bigger and bigger, they cost more energy. And so this mode is going to go up something like that. So this is going to be the case for the transverse fluctuations. Okay, now we have a model here, which is ON symmetric. So now I want to ask, how many of these different modes are there? How many longitudinal modes are there? And how many transverse modes are there? Exactly. So there's going to be one mode that is longitudinal. And n minus 1 modes in the transverse direction. These modes which are gapless, as the wave number goes to 0, these modes are called Goldstone modes. The modes whose energy spectrum E of k goes to 0 as k goes to 0, those are known as Goldstone modes. I'm going to correct this statement in a minute, so don't believe it for now. So let's ask ourselves the question. Okay, great, that's a name. So let's try to see some examples. So you might say, okay, so any mode that goes to 0, like I've shown on the left-hand panel, has an energy spectrum like that. That's a Goldstone mode. Okay, and there's something special about it, which we haven't fully understood yet, but there's something special about it. So let's think of an example of a mode, something that you know about, that you learnt on your mother's knee, which has a spectrum that looks like that. And I give you a clue. I'm using it right now to talk to you. What would it be? Sound. Right. The energy spectrum of sound obeys the wave equation. The dispersion relation for that is omega squared equals c squared times k squared. And so that goes to 0 just like that. So we have one example, which is a sound mode. A sound mode. So this sound obeys the wave equation. And so if it obeys the wave equation, then I know that the omega is equal to ck. And so you might say, okay, so is this a Goldstone mode? Okay, so question, who thinks sound waves are Goldstone modes? You do, EJ, because I just defined it to be like this, and it obviously is like that, right? Okay, anybody else agree with EJ? Okay, you do. Srijit doesn't just, but Srijit doesn't know why he disagrees. He's just disagreeing because he asked the question. Yeah, of course, exactly. Okay, so of course I paid EJ $50 just to say yes for this. I'll give you a check after class. So it's not a Goldstone mode. Okay, it's not true. Okay, there's two reasons why this is not a Goldstone mode. Okay, so who can give me one? So let me just write this down. So what's the first reason? EJ, you.
Because you only depends on the amplitude.
You said it doesn't, it only depends on the amplitude. I don't know. I don't interpret that as being the answer to my question. Okay, so just hold the thought. We'll come back to it when maybe it's what you meant and I just didn't understand it. Okay, Srijit, before you, I know you're bursting to tell me, but somebody else want to answer. Two reasons. Okay, well, we have to move on. Srijit, yes.
I think it's because like the sound is a pressure wave. It's
Yes.
like longitudinal.
Yes, exactly. Sound. So that what you're hearing, the sound mode is a longitudinal mode. So you don't believe it for that reason. Very good. Okay. There's another reason. More subtle reason. By the way, many textbooks get this all wrong. Okay, so this is why we're doing this. There's another reason. Okay, how did I derive these Goldstone modes? What was it necessary for me to do to derive them? Remember, I had to go and find this picture and copy it and paste it into my notes at this point. Why did I have to do that? Justin? No? Anybody? What was special? Julian?
It's a spontaneously broken symmetry.
It's a spontaneously broken symmetry. Okay, this picture on the left, I had to grab it because I was showing you this is what the spontaneously broken symmetry looks like. And we got this mode as a consequence of spontaneously broken symmetry. So this statement here about this thing being a Goldstone mode, just because it's energy spectrum, is complete nonsense. It has to be, so it's not, because it's not a consequence of spontaneous symmetry breaking. Can I have transverse modes in a liquid? No, by definition. If I have a solid, then I can have transverse shear modes. So we might ask, well, if we had a so suppose I have now a solid. I start off with a liquid or fluid. I go below the ordering temperature, and now it becomes a solid. Okay, so I go below the melting temperature. Okay, am I going to get Goldstone modes there? Okay, so I started with a liquid, no Goldstone modes, no spontaneous symmetry breaking. Now I make a solid. Okay, I have spontaneously broken symmetry. What symmetry have I spontaneously broken? Translational symmetry. Right, there's spontaneously broken translational symmetry. So the solid sits there and it's broken the translational symmetry. All the atoms are now some special distance apart, just like we talked about in the beginning of the class. Okay, are there Goldstone modes in that case? Okay, well, let's see what modes are there. So I hit the solid, okay? And what you hear are longitudinal modes, just like the sound modes, but you also hear some modes because when I hit it, I cause a little bit of shear, and so there's some shear modes. And because it's a solid, it has a restoring force to shear. It has a Young's modulus, it has a shear modulus. That is the defining characteristic of a solid. It has a shear modulus. So I have transverse modes, and those transverse modes only exist because the thing spontaneously broke translational symmetry. So I've got longitudinal modes in the solid, which make sound waves, and I've got transverse modes in the solid, which make sound waves. Okay, are the longitudinal modes also Goldstone modes? Julian says yes. Who agrees with Julian? Is he right? Yes or no? Okay, as usual, the answer is no. Okay, the longitudinal mode in the solid is not a Goldstone mode, because if I go through the phase transition to a liquid state, I still have that longitudinal mode. So the existence of that mode was not a consequence of spontaneous symmetry breaking. But the transverse modes did not exist in the liquid. But once I went through the transition, then I was able to have a solid. I was able to support a static shear. It became a solid. It has transverse shear modes, and those are Goldstone modes. So now if we go to, so this is all true up here. This is all true for fluid. If I now go to a solid, and I'm not specifying whether it is a crystalline solid or not. So now what is going to happen, what we just discussed, is that there is spontaneous symmetry breaking. I have longitudinal modes. And I have transverse modes. Those transverse modes reflect the fact that as I go to k equals 0, a solid can support a static shear. If I take a solid and shear it, and keep it sheared like this, it is constantly applying a restoring force to me trying to deform it. That is the definition of a shear modulus. A liquid, if I shear it and just keep my shear like that, the liquid will eventually flow back and it won't exert a force. So the solid, so the existence of a static shear modulus is the defining characteristic of a solid. Not whether it's got Bragg peaks, is this. It's the defining characteristic of a solid. And those transverse modes do not exist in a liquid, but the longitudinal mode, this mode continues to the liquid state. When I'm above the melting temperature. So Goldstone modes are known as Goldstone modes, and so the caveat to this is that they have to, if they exist, as a consequence of spontaneous symmetry breaking. So there's other great examples of Goldstone modes. Those Goldstone modes could be in a magnet, various types of magnons, and so on and so forth. Okay, so just to summarize, so if I have in a solid, so a solid will have one longitudinal mode and then two transverse modes. So I have to worry about the polarization. And only the transverse modes are the Goldstone modes. Okay, so now I want to answer a different question. I want to ask, well, so far we've been talking about the response of the system to perturbations. So now I want to ask, well, what do the correlation functions look like? So up to now, we talked about susceptibility. So now I want to ask, what do the correlation functions look like? We know they're very closely connected, but how? So we're now going to answer that by doing a calculation. So let's talk about the strategy of the calculation. So the first step we're going to do is we're going to take our Hamiltonian, minimize it, and that's going to give us a spatially uniform state. And if I compute the expectation value of the magnetization per spin, that's going to be something that's non-zero. Now, if I want to compute the fluctuations, remember what our trick was from last time. We just do a perturbation about the minimum. We do the perturbation to second order because we know the first order term vanishes by definition of the fact being a minimum. And then from just working out the free energy, working out the Hamiltonian, I can then read off exactly what is the correlation function from that using the equipartition theorem trick that I showed you before. So the second part of the strategy is going to be to compute the free energy cost of a fluctuation about this non-zero mean value. And I'm going to do that in the Gaussian approximation, just like we did last time. And then from that, I can then read off the correlation function. We know it's going to be a bit more complicated because this correlation function is going to be a tensor. And so we're going to have to identify all the components and I'll make it easy for you, but we're going to have to take that into account. And we know that's going to be important because the longitudinal and transverse response and susceptibility are different. And so we're going to ask now, how does that show up in the correlations? Okay, so let's do step one. So step one is I just look at the potential, which I call V of S. I'm going to write it in Einstein's summation convention. So R naught S alpha plus 1/4 U naught, and then S squared, so S alpha, S beta. So that in summation convention is what the potential looks like. So just a reminder is that repeated indices are summed over. Okay, so S alpha means the sum from alpha equals 1 to n S alpha squared. Okay, so I'm not going to write that out each time because it would just get too cumbersome. Okay, so the next thing that we do is we minimize the effective Hamiltonian. So I have to set dV by ds is equal to 0, and I'm just going to do this by looking at the alpha component. So if I differentiate this with respect to 0, I get R naught times S alpha plus 1/4 U naught, and then 2S alpha, and then S beta, and then another factor of 2. Okay, so remember what I've done here is you tell me what is alpha, and then that alpha number appears here on the left-hand side, and then S beta is summed over, so that's a dummy variable. I could have called it hippopotamus or elephant or kangaroo, but it doesn't matter because it's just summed over, and there's two factors of 2 here. So one factor of 2 came from differentiating S alpha squared, and the other factor of 2 came from the fact that I've got S alpha squared S beta squared, so I could equally have got this factor of 2 from differentiating the S beta sums. So there's 2 factors of 2 that come in here, which conveniently cancel out the factor of 4. And so what I get then is that I get S alpha into R naught plus U naught, and then S squared. And that thing has to equal 0. Okay, so that's my ground state. So for t greater than tc, I know that R naught is greater than 0, and so that means that S alpha is equal to 0 for all its components. But for t less than tc, I know that R naught is negative, and so I can also have the solution that says that S squared is equal to what I'm going to call m squared, and that is equal to minus R naught over U naught, and R naught is negative, and so that's a positive number. So all I get from solving the minimum is I find the magnitude of the order parameter, but not its direction. So now we're going to break the symmetry. So we're going to choose a direction of ordering. So I'm going to say that the expectation value of the order parameter S is equal to the magnitude M times some unit vector. And I'm going to choose, without loss of generality, this unit vector to be 1, 0, 0, blah, 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 in the n-dimensional spin space. So now we're going to look at the fluctuations. So step 2, we're going to look at the fluctuations. So those fluctuations can be spatially dependent. So my order parameter now will be a function of space, and it's going to look like this. It's going to equal m times n hat. So it's in an ordering direction, and then there's going to be a fluctuation, and I'm going to call that fluctuation phi of r, and so that is a vector. And just to make life easier, I'm going to multiply it by a factor m, just include that in the definition of m, just to make the algebra simple. So this is going to be how I define the fluctuation. Okay, so now what I'm going to do is I'm going to break phi into a longitudinal and transverse part. So we're going to write that there's a component phi 1, which is proportional to the direction of ordering. And then there's a component phi transverse, which is perpendicular to the direction of ordering, and this is going to be a vector. Now, this is also a vector, but it's just going to be a unit vector. So what we can say then is that phi phi 1 is parallel to m, and phi transverse is orthogonal to m. So I can write this in the following way. So phi transverse is then going to be the vector 0, phi 2, phi 3, up to phi n, and phi 1 is the vector phi 1, and then 0, 0, like that. So that's how I'm decomposing the fluctuation. Okay, so that's the decomposition of the fluctuation. Then the next step is to actually calculate V of S. So V of S is, sorry, not V of S, but I am going to get to V of S in a second. So let me just write down what S is then. So to summarize it, what is S? So S is M, that's the magnitude, and then it points in the direction of ordering. So that's N, that's the first term, the mean value. And then there's a term phi 1, which is also in the direction of ordering. And then there's the term phi 2, which I called phi perpendicular, which is orthogonal to the vector n. So that's how I'm going to write S. Okay, so that's fine, nothing special there. So now we want to compute the energy. So now I want to compute V of S. So what do I get in V of S? Well, V of S has terms S squared and S to the fourth. So let's go and calculate that. So V of S includes S squared and S to the fourth, where those mean the magnitude. So let's compute them. S squared over M squared is equal to 1 plus 2 phi 1 plus phi 1 squared plus phi perpendicular squared. So that's just squaring, that. And then S fourth over M to the fourth, everything scaled by the magnitude of the ordering, that is a whole bunch of terms. So let me write them all out for you, but it's easy for you to check them. So it's 1 plus 4 phi 1 plus 6 phi 1 squared plus 4 phi 1 cubed plus phi 1 to the fourth plus phi perpendicular to the fourth plus 2 phi perpendicular squared plus 4 phi perpendicular squared phi 1 plus 2 phi perpendicular squared phi 1 squared. Did I get them all? So all I did was take the formula for S squared and square that. So I've got 4 terms there, and I've just squared them. And hopefully I copied them down right from my notes. You should check this. So this is just 30 seconds worth of checking. So now let's put it all together. So now let's compute what V of S is. And I'm going to write down for you the answer, and I want you to check this, okay? So I claim that the answer is this. V of S is minus 1/4 R naught squared over U naught minus R naught M squared phi 1 squared plus higher order terms and so that means that they go like phi cubed and phi fourth and so on. Remember, we're only computing the fluctuations to quadratic order because we're just doing Gaussian fluctuations. That was in our strategy right over here. We're computing only in the Gaussian approximation. So I only care about what I can compute to quadratic order, which makes life a lot easier. Okay, so everybody here should check this. Check this for yourself. And it's very important for you to check it. And you'll see why in a minute. Okay, so that's the potential, but that's not the full expression for the energy. We also need to compute the gradient terms. So the gradient terms are 1/2 grad S squared. And let's go ahead and write what those are. Well, S is just a constant vector plus the fluctuations. So the only terms that come from the fluctuations are going to involve the gradient of phi. And those are going to look like this. M squared over 2 grad phi 1 squared plus M squared over 2 grad phi perpendicular squared. So, and again, you should check that. So now we can put it all together. And so, so overall, if I were to write out the effective Hamiltonian for the fluctuations, I'm going to call that phi. That just depends on the vector phi, the fluctuations. And that looks like the following. It looks like the factor of m occurs outside. So that comes out as m squared over 2. I scaled everything by m over here. And we did that to make life easier for ourselves. And then I have the integral over all the space, over the volume of my system. So I have the term grad phi 1 squared. I have the term grad phi perpendicular squared. Then I have the term, this term over here, which is just 2 times the magnitude of R naught times phi 1 squared plus higher order terms. And that's it. So and remember, R naught is negative. And so I can write this term over here, because R naught is negative, I can write it as the absolute value of R naught times phi 1 squared. Okay, so that is the effective Hamiltonian. So now let's compute what it looks like in Fourier space. And we want to write it in Fourier space because we want to be able to read off the correlation functions. So I'm going to write the Hamiltonian. I'm writing down the minus h. So now we're going to take the Fourier transform of this. So everything's quadratic, so it is easy to do the Fourier transform. So let's just write it out using Parseval's theorem. It looks like this: 1 over v sum over k. And now we get 1/2 absolute value of phi 1 of k squared times some stuff, and I'm going to call that stuff G parallel 0 of k minus 1 plus 1/2 I perpendicular of k squared times something, and that something I'm going to write as g perpendicular of k to the minus 1. And I know that those things are going to be the correlation functions because last time we saw that the coefficients of the quadratic terms in k space are just the inverse of the Fourier transform of the 2-point correlation functions. And we've got a correlation function for the longitudinal ones, that's phi1, and a correlation function for the transverse ones, that's phi perpendicular. So let's go ahead and read off what those things are. And we just can read them off by looking over here on the left-hand side. We can see what those terms are when we Fourier transform them. So when we Fourier transform G naught of k, I can just simply read that off. That is m to the minus 2 over 2 r naught plus k squared. And G perpendicular k is equal to m to the minus 2 over k squared. Okay, so that's how we read this off. So all you've got to do here is, where I've got the integral dr grad phi squared, grad phi perpendicular squared, those just turn into k squareds. So the coefficients of phi1, notice over here, let me just point this out to you explicitly. So there's 2 terms for phi1. There's this term, that's going to give me this k squared over here on the bottom over here. And then there's this other term, 2 for r naught phi1 squared. So that's a quadratic term, and that gives me this term over here. So that's where that one comes from. And then this term over on the only term that's left is this one, the only term involving phi perpendicular. And when I take the Fourier transform of that, then I'm going to get k squared, and so that's where that comes from. So that's the origin of those different terms. Okay, so we've discovered something miraculous, and of course all of this is true for t less than tc. So we're looking at the emergent properties of the system. Okay, so now what does it mean? So what we've seen then is, if I look at the longitudinal correlation function, so this thing is supposed to go like 1 over k squared plus psi to the minus 2 times some amplitude, which happens to be m to the minus 2. So let's just say it's proportional to this. We know that it looks like that because k is dimensions of inverse length. So we know that there's an inverse length over here. So we call it psi to the minus 2. And this I'm going to call the longitudinal correlation function. Sorry, longitudinal correlation length. So I'll call it psi parallel. And this is below TC, so I'm going to call it like that. This thing, the minus 2, is equal to 2 r naught. And remember, r naught is proportional to t, which is t minus tc over tc. So what this then tells us is that I've got a longitudinal correlation length below tc, which is proportional to t to the minus 1/2. So that's the first result that we've obtained. So the longitudinal correlations decay exponentially when I take the Fourier transform with a length scale that diverges as t to the minus 1/2 as I go towards the phase transition. Okay. Now, what about the transverse correlations? So this transverse correlation in k space goes like 1 over k squared, which I can think of as being 1 over k squared plus xi perpendicular to the minus 2. But what we've discovered that there's no xi perpendicular. So xi perpendicular to the minus 2 is equal to 0, which means that xi perpendicular is infinity. So what that means is that there is no finite correlation length in the transverse directions. If I take the Fourier transform of 1 over k squared and I'm in 3 dimensions, what do I get as a function of space? What do I get? Do it in your head.
So,
1 over r. Right? So the transverse correlations decay as a power law. And you might say, oh yeah, well, they have power law decay. That's because we're near a phase transition and correlations start to decay as power laws when you get close to TC. But we're not close to TC. This is true for any temperature less than TC. So the transverse correlations have power law decay, and so we can say then that that the transverse correlation function g perpendicular of k has a pole at k equals 0, and this pole corresponds to the Goldstone mode. Okay, so let's summarize that, and then we'll be out of time. So the summary is, okay, first one, T less than TC. Transverse correlations, when you have continuous symmetry, transverse correlations are power law decay, not exponential. For T less than TC, longitudinal correlations have exponential decay with distance. For T greater than TC, the same thing is true. Longitudinal correlations exist and have exponential decay with distance. For T greater than TC, there's no transverse correlations, no transverse fluctuations. And for T equals TC, longitudinal and transverse are power law. Okay, so that's the summary. I'm going to just say one more thing for those of you who've seen quantum field theory. Okay, so back to quantum field theory, which we talked about at the end of last time. In quantum field theory, we have a Feynman propagator in K space, which looks like 1 over K squared plus M squared. That's for a particle of mass M. In statistical mechanics, what we have is we have G naught is 1 over k squared plus xi to the minus 2. And so I can see that the mass in quantum field theory is like 1 over the correlation length in statistical mechanics. Okay, so now in these Goldstone modes that we've talked about, they have the psi in statistical mechanics is equal to infinity. And so that means that as in terms of particle masses, these are massless particles. And these are Goldstone bosons. So the quantum field theory version of this is that this Goldstone mechanism is a mechanism for creating massless Goldstone bosons as a consequence of spontaneous symmetry breaking. Okay, and these are scalar particles. So you have to say, well, there's massless scalar particles. In fact, these massless particles, do they exist? Well, actually, when you have spontaneous symmetry breaking in quantum field theory, at least in the context of the standard model of particle physics, we don't have those. We don't have these massless Goldstone modes. We actually have massive Goldstone modes. Okay. These massive Goldstone modes are related to the Higgs boson that you've heard about, and so we'll say a little bit about that, but not too much in this course. These massless modes exist in superfluids. These massless modes that are not massless but are massive, these massive Goldstone modes, where they come from is when you have gauge symmetry in addition to the continuous symmetry of the order parameter. And we have a homework exercise on that you can work out, so you can see the Higgs mechanism in a non-relativistic context. The Higgs mechanism was discovered in condensed matter physics first. We call it the Anderson-Higgs mechanism. There were many people who can legitimately claim to have basically discovered the mechanism. But the fundamental problem that exists is this: when you look at the Goldstone modes, the spontaneous breaking of continuous symmetry, you should get massless Goldstone modes, and we don't see those. We see massive modes, and that's what we'll talk about some other time. Okay, that's the end of today's lecture. So let's wrap up, and I'm going to turn off the recording.